Let's take a look at some active drug moiety calculations. These include chemicals or drug molecules that are present as hydrates and solvates, as well as those that are present as organic salts. So if you take a look at the table below, especially if we look at this metaproterenol sulfate, you can see that a significant amount of the molecular weight actually is accounted for by the sulfate portion of the drug. So in this case, the active drug moiety, the metaproterenol, has a molecular weight of 211.26. However, the organic salt, present as a sulfate salt, has a molecular weight of 520.59. So a significant amount of the weight is going to come from the salt. So we'll take a look at how to account for that, and then we'll also take a look at some calculations involving moisture. So let's take a look at hydrates and organic salts. So this is just anything where we have some chemical form of our molecule where the molecular weight is going to include something in addition to just the active drug moiety or drug base that we're interested in. So for determining calculations for how much to adjust your measurements, you can just set up simple ratios. So as I have here, we could set up a ratio where we say our weight of active drug moiety, abbreviated A, over the molecular weight of that drug moiety E, can be set equal to the weight of the hydrate or salt, abbreviated W, over the molecular weight of that hydrate or salt, B. So if we're just interested in solving for the weight of the hydrate or salt W, you could rearrange these ratios to give you this. W is equal to A times B over E. If you forget which one goes on the top or bottom, remember if you have something other than just your drug that's accounting for the molecular weight, you're going to need to weigh more than what you would need for just that active drug moiety. So your weight of this hydrate or salt should always be greater than the weight of the active drug moiety. So looking at our first example here, we want to calculate how many grams of the citric acid monohydrate we'd need in order to get the equivalent of 5 grams of anhydrous citric acid. So the weight of our active drug moiety here is going to be 5 grams of that anhydrous citric acid, which has a molecular weight of 192. We can set that equal to X over the molecular weight of the hydrate, which is 210. So if you plug that into your calculator, you come up with an X equal to 5.47 grams. So that's just solving that using a simple ratio. If you wanted to use the kind of pre-rearranged equation shown at the bottom, our W equals A times B over E. We can say our W is equal to the weight of our active drug moiety, 5 grams, times the molecular weight of the hydrate, which is the 210, divided by the molecular weight of the active drug, and we'd come up with the same answer of 5.47 grams. So pretty straightforward. We can also solve for the equivalent weight of salts using the same approach. So in this case, how many grams of methadone do we need to provide 2 grams of methadone? So we want 2 grams of our active drug methadone over its molecular weight of 313. We can set that equal to X over the weight of the hydrate, which is 349. So if we solve for X, we get 2.23 grams. We could also set that up using the equation in the bottom panel. So here our W would be equal to the weight of our active drug moiety, so 2 grams times the molecular weight of the hydrate, which was 349, divided by the weight of the active drug, which is 313, and so we come up with that same 2.23 grams. So either approach works, you just have to use what works best for you. The other thing that you may need to account for is the presence of moisture in your drug product. So this is water contributing to the weight of your drug product that is not accounted for in the molecular weight. So this is different than, say, a hydrate. So what we're going to do is take the equations we've been working with, or ratios, and now we're going to include this new parameter, D, which is the decimal fraction of the dry weight. We're going to include this in the denominator of our equation. So if you were to have something with no moisture present, which is what we've been using in our previous examples, D would be equal 1. So if D equals 1, that means there's no moisture. However, sometimes you'll see on a certificate of analysis that the powder contains X% moisture. So if we had a situation where our product absorbed 2% moisture, we would say 1 minus that 2% gives us a decimal fraction dry weight of 0.98. And so we put that in the denominator of the equation. So let's take a look at some examples using this approach. So here we're needing to account for the milligrams of the aminophylline dihydrate in order to obtain 250 milligrams of anhydrous theophylline. Aminophylline contains 2 molecules of theophylline, and what we're told is that the moisture content of the dihydrate is 0.4%. So what we'll do is we have our W is going to be equal to A, which is the weight that we desire of the anhydrous, so that's 250 milligrams times the molecular weight of the hydrate, so that's 456, divided by our moisture content, so D is going to be equal to 1 minus 0.004, so that's equal to 0.996. So 0.996, and that's multiplied by the molecular weight of our drug moiety, and that's going to be 360 because we have 2 molecules of theophylline present in the aminophylline. So if we go ahead and plug all that into our calculator, we come up with a weight of 318 milligrams. So that wraps up our active drug moiety calculations.